Your agent works perfectly on your laptop. Every tool call returns the right data, the LLM reasons correctly, and the final answer is spot on. Then you deploy it, and the user reports that the agent confidently returned completely wrong information. You check the logs and there's no error, no stack trace, nothing. Just a 200 OK and a bad answer. This is the hardest class of bug in agent development because traditional debugging tools were never designed for non-deterministic multi-step systems. Today, we are going to fix that by instrumenting a LangGraph agent with LangSmith so you get full trace visibility into every decision your agent makes in production. The reason agent debugging is so different comes down to one thing: non-determinism. In a traditional application, if something breaks, you get a stack trace that points you to the exact line, but agents make decisions at runtime. The LLM chooses which tool to call, what arguments to pass, and how to interpret the result. So a failure might not be a crash at all. It could be the LLM picking the wrong tool, hallucinating an argument value, or misinterpreting a tool's response. The bug is distributed across multiple steps, and without visibility into each one, you're essentially guessing. LangSmith is an observability and evaluation platform built specifically for LLM applications. It has three main capabilities: tracing, evaluation, and monitoring. Today we are focusing on tracing, which is the foundation for everything else. When you enable tracing, LangSmith captures every LLM call, every tool execution, and every intermediate step your agent takes, and it organizes all of that into a structured trace tree you can inspect after the fact. The important thing to know is that this happens asynchronously in a background thread, so it adds zero latency to your application. And it works with any framework: LangGraph, plain OpenAI calls, or anything else. A trace in LangSmith is structured as a tree of runs. Think of each run as a span. It represents a single step in your agent's execution. The root run is the top level invocation, and it contains child runs for each LLM call, tool execution, and any function you have decorated. Every run captures the full inputs and outputs, the latency, token counts, and the status, whether it succeeded or failed. This means that when something goes wrong, you can open the trace, walk through the tree, and see exactly what the LLM received at each step, what it decided to do, and where the reasoning went off track. There are three main mechanisms to get tracing into your code, and they work together. First, you set environment variables LangSmith tracing equals true and your API key, which activates the tracing pipeline globally. Second, for any custom function you want to appear in your trace tree, you use the traceable decorator from the LangSmith SDK. This automatically creates a run for that function, captures its inputs and outputs, and nests it correctly under whatever parent called it. Third, if you're making direct OpenAI calls, you can use wrap OpenAI to automatically instrument the client. And if you're using LangGraph or langchain, the integration is even simpler. Tracing is picked up automatically once those environment variables are set. The debugging workflow with LangSmith looks like this. You run your agent, and every execution gets traced automatically. When a user reports a bad result, you open the trace in the LangSmith dashboard and walk through the run tree to find the exact step where things went wrong. Maybe the LLM hallucinated a tool argument, or maybe it got a valid response but misinterpreted it. Once you have identified the faulty run, you fix the underlying issue, whether that's a prompt change, a tool output format fix, or a guardrail. And here's the part most people skip. You should save that failing trace as a test case in an evaluation dataset so you can run regression tests to make sure this specific failure never happens again. Alright, that's the theory. Now let's build a LangGraph agent from scratch, instrument it with LangSmith tracing, trigger a realistic failure, and then walk through the entire debugging process using the trace tree. Let's start by setting up our project. We create a new folder called LangSmith debug. Let's move inside of it, and let's create a new Python virtual environment. We also need to activate our virtual environment. Once we have our virtual environment active, we need to install a few dependencies. We're installing LangGraph for our agent framework, LangChain OpenAI for the LLM integration, and LangSmith for tracing. The python.env package will handle loading our environment variables from a .env file. When we have all of this set up, we create a new file called .env. Here we put our required environment variables. We set LangSmith tracing equals true. This is what activates tracing globally. Without this, nothing gets locked. The LangSmith API key is your key from the LangSmith dashboard under settings. And LangSmith project lets you organize traces into named projects, which is useful when you have multiple agents or environments. I'm calling ours agents debug demo so we can find it easily in the dashboard later. Next, we create a new file called agent.py. Let's set it up with all the imports that we need. We load the environment variables first using .env, then import the LangGraph and langchain components. Notice we're importing traceable from LangSmith. This is the decorator we will use to create custom spans in our trace tree. We are also importing toolNode and tools condition from LangGraph pre-built module, which gives us the standard React style tool calling loop without having to wire it up manually. For our LLM, we initialize ChatOpenAI with GPT-4o Mini and temperature 0 to keep responses deterministic, which makes debugging much easier since you can reproduce the same trace. Now we define our tools. I'm creating two tools here. A search docs tool that simulates documentation lookup and a get status tool that simulates checking a system's health. The key detail to notice is the tool decorator, which LangGraph uses to register these as callable tools. LangSmith will automatically trace these tools calls because they're part of the LangGraph execution. But watch what I am doing with the get status. I am deliberately introducing a subtle bug. When the query mentions the word billing, the tool returns an ambiguous response that says the system is operational but with degraded latency. This is the kind of output that won't throw an error but will cause the LLM to misinterpret the status and give the user a misleading answer. This is exactly the type of silent failure that's impossible to catch without tracing. Now we wire everything together into a LangGraph state graph. We bind our tools to the LLM so it knows what's available, then define the call model function that invokes the LLM with the current message state. The graph structure follows the standard React pattern. Start at the agent node, use tools condition to decide whether to route to the tools node or end the conversation, and after the tools execute, loop back to the agent to process the results. This entire graph execution will be traced automatically by LangSmith because we set the environment variables earlier. Every node transition, every LLM call, and every tool execution will appear as a run in the trace tree. This is where the traceable decorator comes in. I'm wrapping our agent invocation in a custom function called handleUserQuery. By decorating it with traceable, this function will appear as its own run in the trace tree, acting as the root span for each user interaction. I'm also passing metadata with the user ID and source, which gets attached to the trace and lets you filter the search traces in the dashboard later. This is a pattern I would like to recommend for any production agent. Always add metadata for the user ID, session, and request source so you can find specific traces when a user reports an issue. Now let's run two queries to generate traces. The first one asks about refund policies, which should work correctly. This is our baseline. The second one asks about billing service issues, which is going to hit our bug. The agent will call get status, receive that ambiguous response with the degraded latency node, and the LLM will likely tell the user that there's an issue even though the status technically says operational. After running this, both traces will appear in our LangSmith project and we can compare the clean trace against the buggy one to see exactly where things went wrong. Now let's test everything. In the terminal we type python agent.py and execute it. As you can see, query 1 said that the refund policy allows for a full refund within 30 days. But query 2 says that the billing service is operational, but it is experiencing degraded latency with a 99th percentile response time of 4200 milliseconds. That's the thing that we want to trace in LangSmith. And now this is what the LangSmith tracing page looks like. Here on the top you can see our two questions. The first one is what is the refund policy, and the second one is the billing service having issues. This is the question that produced the silent issue. Let's open it. As you can see, here we have many different things like start time, end time, status, whether it succeeded or not, how many tokens were used, and what was the price of the query. Let's now have a look. At the top is our handleUserQuery span, and nested inside is the LangGraph nodes. The first agent call, where the LLM decided to use the getStatus tool, then the tools node, showing the actual tool execution, and its return value, and then the second agent call, where the LLM interpreted the result. Now when we look at the tool output, we can see where the issue is coming from. The getStatus tool returned degraded latency, and when the LLM saw degraded latency and it interpreted it as a problem, even though the overall status was operational. Without this trace, you would have no idea where the misinterpretation happened. Now that we have identified the root cause, the fix is straightforward. We have two options. The first is to clean up the tool's response so it's unambiguous. If the status is operational, don't include performance metrics that could confuse the LLM. The second option, which I would recommend, is to add system prompt that instructs the LLM to treat operational as healthy regardless of latency nodes. Let me show you the toolfix. Here in the get status code, we replace it with the updated version. We restructure the response to include a clear healthy boolean that the LLM can use as the primary signal, and we move the latency detail into a separate details field that's clearly labeled as informational. Now let's run our agents once again and verify the output. As you can see, the answer to the second question now is much better. It says that the billing service is operational and healthy, but it is experiencing elevated latency, which is still within the service level agreement. That's fantastic news. We have identified and fixed the issue. Let's recap what we covered. First, we established why agent debugging is fundamentally different from traditional debugging. Agents fail silently because the bugs aren't crashes. They're bad decisions distributed across multiple steps. Second, we instrumented a LangGraph agent with LangSmith tracing using just a few environment variables and a traceable decorator, which gave us full visibility into every LLM call, tool execution, and decision point. Third, we walked through the full production debugging loop, run the agent, inspect the trace tree, pinpoint the faulty step, fix the root cause, and verify with a new trace. From here, I would like to recommend exploring LangSmith's evaluation features so you can turn those failing traces into automated regression tests, and check out the Insights agent feature, which can automatically categorize failure patterns across all your production traces. If this was useful, subscribe to Byte Builder for more practical agent engineering content. I'll see you in the next one.